This is a question where an electron in a hypothetical atom goes from a high excited state, n equals 3, to a low excited state, n equals 2. In the process, it loses energy. It emits that energy in the form of a photon.
The first part of the question is to outline why both states have negative potential energy. So the nucleus has a positive charge, and an electron has a negative charge. From electrostatics, the potential energy of two charges is K, Q1, Q2 over R. Now, since they're opposite charges, this energy for U will yield a negative number. Another way to think about it is that this electron is electrostatically bound to the nucleus. So if I go somewhere far off in space, where U equals 0, where the electron would have no potential energy to do anything else, well, it would take positive work to move the electron there. And that's doing positive work just to bring the electron to a place where U is 0. So since it takes positive work to get to 0 energy, that means the electron must have negative energy in the nucleus. So we can say that the electron is electrostatically bound to the nucleus, which means it has negative energy, and that it would take positive work to separate it from the nucleus and get to where U equals 0.
Part B is pretty simple. It just asks why a photon is emitted in the process. Now this is a process where the electron loses energy. It goes from energy -1 electron volts to an energy of -3 electron volts. So in the process, it lost 2 electron volts. As a result, it's going to emit a photon, and that photon has an energy of 2 electron volts as well. Part C simply involves calculating the wavelength of the photon emitted. So in emitting the photon, the electron goes from energy level n equals 3 at -1 electron volts to n equals 2 at -3 electron volts. So in the process, it loses -2 electron volts of energy, and it loses energy because it's getting closer to the nucleus of the atom. Now I want to use that energy in joules, not electron volts. So to convert, you multiply the number of electron volts times 1.6 times 10 to the -19 joules per electron volt. And that's because an electron volt is the amount of energy that one electron has when given 1 volt. So the energy of the photon would then be 3.2 times 10 to the -19 joules. And then to solve for the wavelength, I'm going to use the fact that energy of a photon is Planck's constant times its frequency. And then I'm dealing with wavelength. So the speed of a photon, which is c, equals f lambda. So then frequency would be speed of light over lambda. And then solving the whole expression for lambda, I get Planck's constant times speed of light over the energy of the photon. And then plugging in numbers, you get 6.22 times 10 to the -7 meters. And then the wavelength of a photon is usually given in nanometers. So the answer is 622 nanometers. Part D involves an atom, which emits the photon from part C. It emits it in the same direction it's going, which is to the right, and as a result, it's going to slow down. Because the atom and the photon are a system with no external forces, momentum is conserved in this case. So before, when the atom is moving, it has a momentum of mass times its initial velocity. Afterwards, it has a momentum of mass times a slower final velocity. And then even though the photon doesn't have mass, it does have a momentum. The momentum of a photon is given by Planck's constant over the wavelength of the photon. So in order to solve this, you just equate the initial momentum, mvi, to the final momentum, mvf, plus h over the wavelength, which is the photon's momentum. Solving that equation for the final velocity of the atom yields initial velocity minus h over m lambda. and then plugging in numbers, you get a final speed of 499.86. So the atom does slow down. A photon does have momentum, but it's not a large momentum, so it only slows down by a very small amount.